Hi, everyone. So let me just share the presentation. Okay, so as Felix kindly introduced, today we'll talk about a particular application of the nanofraser of thermal lithography that is used for patterning magnetic materials. So whereas in most nanofraser applications, let's say, there is a resist that is patterned and then a pattern is transferred into the desired material. In this case, we use a different approach. So we directly use the tip for writing magnetic structures. So we use the heat for modifying locally the magnetic properties of suitable materials in order to be able to control basically their magnetization direction, as I will show you. So first, I would like to thank all the people that collaborated throughout the years. The work started, I think, in 2013, the first demonstration was, and then it went on different substrate and for different applications. But these are all the people that collaborated, starting from the people in Politecnico, and Daniela Petti and Riccardo Bertacco, and of course, Elisa Riedo, that was at the time in Georgia Tech and now is in NYU, where the project actually started. Then our collaborators in Perugia, in Switzerland, always in the US, in Spain, and also in Zurich, in IBM, and with Swisslit. So this is the outlook of the presentation. First, I will talk about the motivation for our work, a little bit more in general than the particular application that I will talk about. And the motivation is to try to find new ways for tailoring the physics of material at the nanoscale for building new materials. Then I will talk about the specific technique that we developed that is used for patterning spin textures. So zones of the magnetic materials with a well-defined direction of the magnetization using the heated tip. And then a particular application of the spin texture that is for manipulating the dynamics of the magnetization, and in particular, a specific kind of dynamics of the magnetization that is called spin wave, that are propagating perturbation in the spin texture of the ferromagnetic materials. So first of all, about the motivation, these are all the systems that we're kind of interested into in these days. And the idea is that there has been a huge boost in the discovery of new materials and new physical phenomena that may benefit from the ability to control them at the nanoscale for building new devices, new materials, new metamaterials for controlling the interaction of quasi-particles like magnons, like photons of electrons, or simply for the ability to find new physics that lives only in these particularly nanostructured materials. And these are some of the physical, let's say, discoveries that we are interested into. Spin waves, of course, that I will introduce briefly. Topological particles, if someone heard about skyrmions, for example, there are topological spin textures that live in ferromagnetic, and not only ferromagnetic, but in general in magnetic materials that can be used for data storage, for example. Spin orbit torques, always in magnetism, and some topological states and van der Waals materials. So in general, we are interested in finding new ways for controlling the physical properties of these materials in a way that is not easy or straightforward to do with conventional nanofabrication. And the application, of course, is to be that are then used for having enhanced functionality in new types of devices. And the technique that we use, that you know very well, is thermal scanning probe lithography. So thermal scanning probe lithography, I will go really fast on this, is based on using a heated tip that can be heated controllably with a high degree of precision in temperature. And since the tip of the nanofraser of the AFM ideally ends up with a spot that is a few nanometers in size, if you have this controlled hot spot that you can move around the sample with high precision, that you can produce all kinds of chemical and physical reactions that are mediated by temperature. Or you can make some reactions that will happen in any case really faster, and so that actually you promote this reaction only in the place that you are heating on the sample. These are a few examples from the past experiments. One of the first ones, I guess. This was in Elisa Riedo's lab, where they changed the conductivity of graphene oxide by heating locally with the tip. This was the first, I think, demonstration of 3D topography with a nanofraser in a polymeric resist. And then we can use it also for biology, for controlling the protein gradients that we can immobilize on the sample by locally exposing controlled concentrations of amine groups, chemical groups in this case, that actually act as sticky points for proteins. And we can use it for building 2D devices on 2D materials, such as transistors in this case. So our idea was to try to use thermal scanning probe lithography for magnetism. And if you want to use this technique for magnetism, then you have to find a physical mechanism that actually is triggered by temperature. And one of the most famous ones, let's say, that are already used, let's say, at the macroscopic scale in magnetic devices is the exchange bias. So exchange bias, in the most simple version, happens at the interface between a ferromagnetic material and an antiferromagnetic material. So here we start with a simple ferromagnetic material. This is the hysteresis loop. So basically the direction of the magnetization as a function, I see something in the chat. So here you have the direction of the magnetization as a function of the external field that you apply. And if you apply a high enough field, then you align all the spins in one direction. Then you go on the other direction and you reverse the spins. But as you can see here, you have two different states at zero external field, which means that you can actually, depending on the history of the field that you can apply, you have two different remanence states, because the loop is centered around zero. But then if you put, let me see if I can, okay, if you put an antiferromagnetic material on the underneath the ferromagnetic layer, then you shift the hysteresis loop and you end up having, due to this exchange bias effect that happens at the interface. So at the you end up having at zero external field only one possible state in the ferromagnetic material, which phenomenological means that you're pinning the magnetization in one direction with respect to the external field. So the nice thing about this is that it is triggered by temperature. So that this is what happens normally at the macroscopic scale. If you start with a low temperature, so for example, your sample at room temperature, you have your ferromagnetic loop shifted, you have only one state, and you have that the antiferromagnetic material pins the magnetization of the ferromagnetic layer, in this case in the left direction. But then if you heat up the sample above the blocking temperature of the system, you temporarily destroy the antiferromagnetic order, so you destroy the interaction that blocks the ferromagnetic material, and you retrieve your originally centered hysteresis loop. Then if you apply an external field while cooling down below the blocking temperature, you can rewrite the magnetization and the exchange bias in the direction of the applied external field. So that by combining heating and the application of an external field, you can actually rotate the magnetization as you want in your ferromagnetic material. And this is conventionally done at the macroscopic scale by heating up, for example, in an oven or on hot plates in presence of an external field for blocking the magnetization of the whole film in your chip in one direction. So our idea was simply to perform the very same mechanism, but at the nanoscale with the heated tip. So you start with your uniform exchange bias sample, where the antiferromagnetic layer at the room temperature pins the magnetization of the ferromagnet all in one direction. Sorry. And then we apply an external field, which is different from the direction of the magnetization of the original pinning. And then we sweep the heated tip on top. And right underneath the tip, the temperature goes above the blocking temperature. The antiferromagnetic layer is locally destroyed. And when the tip moves away, so for example, in this region, you see that we rewrote the exchange bias interaction according to the direction of the external field. So that by performing this, you can actually have different magnetic domains when you remove the field and when you remove the tip, where the magnetization points in the direction of the field that you used for writing. And importantly, you only rewrote the magnetization direction in the place where you swept the tip. So the resolution in this case is, depending on the material, but in the best case is comparable to the resolution of the heat profile, which is a few nanometers. And you can actually create this domain structure across the film, where in each domain, the magnetization can be placed in the direction that you want according to the direction of the field that you apply. And it's a simple technique, or reasonably simple technique. So it's a single step. It's non-destructive because we are simply temporarily destroying the interaction. But then when you cool down the system, it goes back to normal. So basically, you can perform this over and over again on the same spot. And it does not deteriorate the system if you don't go too high in temperature. It works in ambient conditions, so it can work also outside the clean room in air, basically. And as I was saying, you can write reconfigurable structures, and it's robust versus external field, as I will show you, and it's tunable. So these were the first results that we obtained. Here you see a magnetic force microscopy image that shows you the magnetic domains written by tam-SPL. And here you see the corresponding topography. So as you see, you don't see anything in topography because we're just changing the magnetic structure, the spin structure in the ferromagnetic material, and we're not actually changing the topography. So here you see that this is a zoom in of this area. So you see that we wrote different magnetic domains with a magnetization orientation, which is this white arrow, that is opposite with respect to the magnetization orientation outside the written domains. And here you see that depending on the shape of the patterning regions, we can have different shapes of the magnetic domains and different dimensions. In this case, it's 1.5 micron up to 2.5 micron. And you can have square domains, triangular domains, or rhomboidal domains in this case. And this is done by raster scanning the tip, exactly as you would do with conventional nanophaser lithography in this shape. But then if you have a single pass of the line, you can write line shapes domains. And in this particular material, that is iron cobalt boron with the antiferromagnetic layer on top of a, I think, 5 nanometer thick iron cobalt boron layer, you can have a magnetic domain with a reasonably minimum size of 250 nanometers. And it's worth noticing this is not the resolution of the heat profile. This is the resolution that is given by the magnetic properties of the materials that are limited by the width of the domain walls. There are the regions that separate two different domains. So that actually let's say, the thermal profile can be much narrower, but then the magnetic domains cannot be that much narrower because of the magnetic properties of the ferromagnetic layer. And not only we can write magnetic domains, but we can also have an interesting control on the regions that I was saying separate two different magnetic domains that are called the domain walls. And as I will show you later, domain walls are a very important part of magnetic devices that recently have gained a lot of attention because of their ability to really control the flow of magnons, the flow of spin waves in different ways, for example. So domain walls in general, if you heard about racetrack memories, for example, there are recent proposals of a spintronic device for actually storing magnetic information. Well, the magnetic information in that device is actually stored in the domain walls. So this is to say that domain walls and regions in general that separate uniform magnetic domains are very important in the spintronic community. And here you see just some simulations that show point by point locally the spin direction in each point of the structure. So here you see what happens in the square domain, for example. And you see that inside the domain, the spins are all, the arrows are a little bit small, but maybe you are able to see them. They all point in one direction, that is to the left. And then outside, they point all in one direction, that is to the right. And in the regions that separate this uniform magnetization direction, you have a coherent rotations of the spin from one direction to the other one. And this is exactly a domain wall. And you see that depending on the position, you have completely different spin structures within the domain wall. Here you have what is called, in this region, you have what is called a tail-to-tail domain wall, because basically the two domains have the magnetizations that are pointing in this direction. This is the tail and this is the other tail, so they point in this direction. Here you have a head-to-head domain wall, so they point like this. And here you have a side-to-side domain wall, so like this. And all these different spin structures have different functionalities. And so if you can really control the position and the spin structure within the domain walls and within the domain, you can hope to build new devices that exploit this particular properties. And of course, changing the shape, you have different structures at the boundaries. This is what happens when you apply an external field, and you see what happens to the patterns as a function of the external field. This is a magnetic image that is that exploits an effect that is called the magneto-optical Kerr effect, that allows you to basically visualize the magnetization as black and white contrast. So when you see black, the magnetization points towards the left, and you see white, it points towards the right. And you can see that by changing the magnetic field, you can actually modulate the shape of the domains. It's like a breathing motion. And when you reach a high enough field, you actually rotate all the magnetization in the direction of the field. But then when you go back to zero, you retrieve your original pattern state. And this is because the information of the shape of the pattern is actually written in the antiferromagnetic layer, which is not the one that you visualize here. So that when you remove the field, you go back to the original patterned configuration. And the interesting thing in this case is that by applying a field, you can actually change the size of the domains. And changing the size of the domains actually means that you're moving in a controlled way the domain walls that separate the internal domain with the outside non-patterned region. And if you imagine that the domain wall is actually an active component of the device, by applying a field, you can move it really precisely. And so you can have, as I will show you later, a reconfigurable device that you can control with an external field, for example. This is that I was talking about tunability. And these are all the ways that we can modify the parameters of the patterning in order to tune the properties of the pattern itself. So by changing the temperature of the tip, we can change the exchange bias strength. That is basically the shift, the entity of the shift in the hysteresis loop. And the more the loop is shifted with respect to the external field here, the more the magnetization is strongly pinned in that direction. So that if we change the temperature, we have a way to actually tune the strength of the pinning. Another, which is probably the most used way of tuning the pattern is to change the direction of the external field that we apply during patterning. So depending on the direction that you apply, and you can, of course, change the direction of the field while you're patterning, then you can actually change the direction of the pinning of the magnetization with the resolution of the single heated spot. And this is what I will show you later. And you can write, erase, and rewrite patterns. In this case, you see that we wrote two squared patterns with the direction of the magnetization opposite with respect to the outside region. Here, what we did was to erase only one of the squares by performing the pattern again with the direction of the magnetization exactly of the external field during patterning exactly the same as the direction of the magnetization outside. So effectively, we removed the pattern, and then we perform patterning again in the original direction, but with a different shape, in this case, a triangle. So by using, let's say, these two particular properties, we can go on and write something more than magnetic domains and magnetic domain walls that may also be interesting for data storage, for example. So if we start with a uniform domain, so a non-pattern domain, and we write a single domain here, for example, by tam-SPL, with a magnetization direction that is opposite with respect to the outside magnetization, then, as I showed you before, we also stabilize the domain, but we also stabilize the magnetic domain wall. And the magnetization, so this rotation, coherent rotation of spins in this domain wall can be towards the right or can be towards the left. And there's nothing that tells the magnetic material in which direction this domain wall should turn. But then we can actually use tam-SPL again to rewrite the top part and the bottom part of the region that we are patterning. And according to the direction of the magnetization of the two top and down domains, the magnetization of the domain wall, that is called the chirality of the domain wall, is fixed in the direction of the magnetization of these domains. So that's actually what we did, was to exploit the boundary conditions at the at the two ends of the domain wall for fixing the magnetization within the domain wall. But then we can do the exactly same thing, but instead of writing one, let's say both the domains with the same magnetization direction, we can write, for example, the top domain towards the right and the bottom domain towards the left. And what happens is that the domain wall doesn't know what to do, because it cannot stay all magnetized in this direction or the other one. And so what happens is that the bottom part has a chirality that is consistent with the bottom domain, and the top part has a chirality that is consistent with the top domain. And this means that necessarily, for a topological reason, in the middle of the domain wall, or in any position actually in the domain wall, there must be a topological texture that is called a vortex in this case. And the nice thing of this way of stabilizing these vortices is that you have a really precise control on the topological properties of the vortices. That is the vorticity, so the direction, the type of vortex that you write, or the chirality of the vortex, so the direction of whirling of the vortex. Now I show you a couple of experimental examples. So this is exactly what I show you in the previous slide, and this is the experimental magnetic force microscopy image that shows that basically here we have stabilized a clockwise vortex where the magnetization rotates in this particular point in the clockwise direction. And the direction of the vorticity is decided via tam-SPL by the direction of the magnetization of the boundary conditions that you write in the domains. And this is a micromagnetic simulation that shows the whirling of the spins around the vortex. But if you change the direction of the magnetization at the boundaries, you can write a completely different topological texture that is called an anti-vortex, where actually the spins, as you see, don't whirl in one direction, but have this particular way of stabilizing themselves, which, to see in a few words, you have these two portions that points toward the center and these other two portions that are exiting from the center. And you can deterministically choose between these two by choosing the boundary conditions. And if you see what we saw before here, you see that all these points on the domain wall where the vortex is stabilized actually act at possible metastable points for the vortex, which means that if you write a curved domain wall, for example, and you stabilize a vortex in the middle, then by applying a field or a current, you can actually move this topological texture around using the domain wall as actually a racetrack for moving these topological textures. And this is just simulations, but shows you that you can actually use fully patterned, let's say, magnetic materials for having vortices and the track where the vortex actually can be moved on. And this may have applications for data storage, for example, because as I was saying, racetrack memories are something that people are trying to, let's say, engineer and optimize right now. So far, I showed you, let me go back one second. So far, I just show you tam-SPL in this particular system, which is the most simple system that you can have, where you have only one ferromagnetic layer and one antiferromagnetic layer that provides the exchange bias effect that you need for tam-SPL. But you can also complicate things a bit, and you can have different magnetic systems, for example, composed by two ferromagnetic layers, which are point-by-point oriented antiparallel one to the other one. So this is called the synthetic antiferromagnetic system, because you have two ferromagnetic layers that are point-by-point oriented in the opposite way in one respect to the other one, which actually is something that mimics what happens in antiferromagnetic materials, but at a, let's say, whole film level. So what happens here is that you have your usual antiferromagnetic exchange bias interaction on the top layer. So you can write, again, by tam-SPL, the magnetization in the top layer. And you know, because of this interaction that happens between the two ferromagnetic layers, that the bottom layer will point by point adjust in the opposite direction. And so you can write, again, domain walls, topological textures within domain walls or magnetic domains, exactly as we did before with a single magnetic layer. But in this case, the magnetic configuration is a little bit more complicated because you're actually controlling not only one layer, but also the direction of the second one. And this allows you to actually play with this system in a different way than what we did with the first one. And I will show you that in this particular system, we have a different applications for the spin textures in this case. The last system that I want to show you about, this is something that we haven't published yet, is that you can perform the very same patterning also in out-of-plane systems. Now, out-of-plane systems, so where the magnetization points out of the plane of the film instead of in the plane, are interesting for a lot of applications. Actually, most of the applications that I talked about before are actually optimized for out-of-plane magnetization systems. So, for example, racetrack memories are actually working in this case. Fermions are actually stabilized in this particular system. And the idea is that if you have the exchange bias effect with the antiferromagnetic layer that acts on an out-of-plane magnetization layer, then you can perform the patterning again also in this system. And in this case, instead of having magnetization direction within the plane, you can write magnetization out of the plane or within the plane of the film. And here you see some example of magnetic domains that we've wrote, square magnetic domains, where you see the black contrast means that the magnetization points within the screen and the white contrast points towards you. And you can, again, write different shapes and actually control the spin texture within the film pretty much as we did in the previous layers. The interesting thing is that in this particular system, there's not only the exchange bias interaction, but there is another interaction that is called the Alonjinsky-Moria interaction that actually causes the domain walls to be chiral. There is a particular property that allows you to stabilize this magnetic skyrmion that we actually talked about before. So that actually what we're doing here is to write magnetic skyrmions with a well-defined shape and location on the sample. And this is the spin texture that actually represent a magnetic skyrmion. And so that if you can write this let's say, skyrmion phase point by point in your material, that you can actually have hope to control the skyrmions by currents or by fields, and to actually build some also logic devices that actually exploit the motions of these textures that you can stabilize in the film with current or external fields. So to have let's say a sum up of the first part of the talk, I'll show you that you can actually use the heated tip in combination with the exchange bias effect in 3 different systems. So the in-plane system, the out-of-plane system, and more complex system composed by multiple ferromagnetic layers that are coupled antiferromagnetically one to each other. And you can use tam-SPL depending on the shape that you pattern and on the particular direction of the external field that you apply during patterning for writing magnetic domains, domain walls, or topological spin textures such as vortices or anti-vortices. Now we come to the main application, let's say, that we investigated so far. That is, let me see if I can start the video here. Okay, that is maybe. Okay, that is spin waves. So spin waves are propagating perturbations in the spin texture of magnetic materials. Here you see an example of a spin wave. So if you have a ferromagnetic material and you provide a really localized magnetic field excitation, exactly as you would have by throwing a stone in a lake, then you have ripples in the direction of the spins. And these ripples propagate as waves, and hence the name spin waves, that propagate within the magnetic materials. And the interesting thing about spin waves that may be interesting for computation is that they have a wavelength that can be down to the nanoscale in a range that's conventional, let's say, that the electromagnetic waves are much larger. So for example, in gigahertz or terahertz range, they have a wavelength that can go down to the nanoscale, a few nanometers. The other thing is that being a motion of the spins, there's no really a motion of charge involved. And if there's no motion of charge, then you don't have Joule heating. And so you have a low energy dissipation. So you have that these waves do not, the propagation of these waves do not involve the motion of charges. And so you don't have Joule heating dissipation. And then you have a very rich phenomenology, which is kind of also a drawback in some situation, because it's extremely complex to control all the parameters involved in spin waves to be able to really manipulate them and being able to build devices with them, because the phenomenology, it's so rich that you can sometimes, or let's say, overwhelmed by all the interaction that are involved in spin waves. For one example, is that spin waves actually can interact with themselves. So are naturally nonlinear, and so you can actually have, for reasonably high intensities, a lot of nonlinear effects that in some cases you can use for building non-conventional computing platforms, but in other cases are detrimental, for example, to your linear interference pattern. So you have to really control very well the systems where the spin waves are propagating into to be able to use spin waves for computation. And there are two, let's say, main paradigms that you can use for making computation. You can either have let's say, a digital paradigm in which you have, for example, a logic gate, so with a binary input and binary output, that actually works. Instead of using transistors cascaded one with each other, you have logic gates that actually work by using the interference of spin waves that propagate in confined conduits. So you have basically waveguides. You excite spin waves as an input. Here, they interfere somehow depending on the shape of the conduits and how they're joined with each other. And then you have an output that is basically high amplitude or low amplitude that depends on the interference and on the spin wave path that each one of the input has. And you can basically have a logic function by building this kind of structure. Another kind of different paradigms is to use spin waves for analog computation. So instead of having a digital output, we have a whole continuum of amplitudes and phases usually in a extended chip, so that we can use extended spin wave interference figure to actually perform, for example, Fourier transforms or signal processing more in general. And this is a first simulation of device that actually excites spin waves in this location, and the different exciters actually produce the interference pattern within the film. And then you pick up the signal in different positions of the chip, and depending on the position, you basically pick a different frequency of the spin wave, and so you have a spectrum analyzer basically, but using spin waves instead of, let's say, conventional electronics. These are the two, let's say, big paradigms for spin waves. And now comes why we can actually do something about spin waves with tam-SPL. And this is because one of the rich phenomenology part that I told you before is that spin waves are highly anisotropic with respect to the direction of the magnetization where they travel into. So, for example, this is a striking example. If you have this sea of spins all aligned in one direction and you throw your stone into the lake, then you have ripples that propagate from the point of excitation to the shore. But then depending on the direction that you consider with respect to the magnetization, so this direction or this direction, the wavelength is completely different. And not only the wavelength, but the whole dispersion of spin waves is really different. Which means that if you can control point by point the direction of the magnetization, you can also control the properties of the spin wave that are propagating. And not only the properties of the spin wave that are propagating, but also the way that they are excited point by point. So that basically by controlling the spin texture, you have a powerful and reconfigurable way to actually build devices that concern both the generation of spin waves, the propagation of spin waves, or the modulation of the spin waves that are already propagating in the film. And so our, let's say, original was to build what we call the magnonics in a domain. So to use actually magnetic domains and spin texture as active components in magnonic devices. And you have to think that normally all the magnetic domains in the ferromagnetic layer cannot be controlled very well. And usually the thing that is done is that you have to apply an external field to have the least domain possible in the film so that you can control spin waves very well. Our idea was to do the opposite, actually. So to create artificially different regions, so different domains, in order to use these regions for actually controlling the generation and the propagation of spin waves. And here you see, again, a very naive example of what we could do. So to have a magnetic domains where we have spin waves propagating only on the edge of the magnetic domain, and then recombining at the end to build something like a Mach-Zehnder interferometer for spin waves, but instead of having to pattern the waveguides and to actually craft the material, you have it in the magnetic domains. All the functionality is in the magnetic domain, which means that if you rewrite the domain in a different way, you can have a completely reconfigurable functionality. So we tried to go in this direction, and we basically first, before to do the domain thing, we had to see what happens at each single domain wall. So instead of focusing on what happens within the magnetic domain, now we focused on studying the spin waves at the boundaries of the domain, so at the domain walls. And for doing this, you really need a high resolution patterning, and we use the tam-SPL technique. And you also need a high resolution imaging of spin waves. And for doing this, we went to PSI, to the Swiss light source, that have a really incredible technique that actually allows you to see videos of spin waves propagating within the material with an extremely high spatial resolution down to 20 nanometers, and with a high temporal resolution, so up to a few gigahertz. So we can actually write the magnetic domains and then go to observe, excite spin waves with an antenna that I'll show you later, and then observe point by point how the spin waves propagate within the domain wall. So these were the first two examples. So we had our antenna here, and we have a pattern domain wall where you see it's here, where the magnetization on the left points towards the bottom, and the magnetization on the right points towards the top. And here you see a micromagnetic simulation that shows you point by point the direction of the spins. And you also see that in the domain wall, the spins are, again, coherently rotating from one domain to the other one. But you can also, if you shape your patterning in a suitable way, you can also write curved domain walls. And so here we wrote pretty much the same structure, but instead of having a straight one, we have a curved one, so that here the spins rotate from here to here in a controlled way across the curve that we set with the shape of the heated tip on the sample. And here we are using the first system that I told you about. So a single ferromagnetic layer exchange bias with an antiferromagnetic layer. So we went to the synchrotron to see what happened. And here we see that we can actually, so here you see spin waves as black and white contrast, and the gray is where there's no spin waves. So you could see that on the straight domain wall, you can see spin waves propagating, exciting where there is the strip line. This is the RF antenna that we use for exciting spin waves that propagate in this direction away from the antenna and are localized only at the domain walls. And you see the same also in the curved structures, where we can excite spin waves from the antenna and have the propagation of the spin wave that leaves the antenna and goes and follows the domain wall very nicely. So this means that actually by writing domain walls, we can write basically waveguides for spin wave that can take spin waves on the chip and along curves on the chip as we wish. And here is the complex geometry of the spin wave that I will not go too much in detail, but basically, phenomenologically, these spin waves are wiggling motions of the domain wall. So you have to imagine that the static domain wall is it's like a straight line. And when you have a spin wave, this domain wall, as you see here in the simulation, does like this. And within the domain wall, also you have a coherent rotation of the spins within the domain wall. But then we went to something more complex. So since we know that a domain wall acts as a waveguide, then we can combine two waveguides, pretty much like in the naive picture of the magnonics in a domain concept. So we write a magnetic domain that comprises two domain walls. And for doing so, we wrote the direction of the magnetization outside. Yes, basically, we took a sample with the direction of the magnetization pointing towards the bottom, and then we wrote this magnetic domain with the magnetization direction pointing towards the top. And then we went to see what happens. And we saw that when the two domain walls are separate from each other, then we have the two spin waves that are, let's say, independent one to the other one because they're spatially separated, that propagate here and here. And here, if you have a profile of the spin wave amplitude that you see here, this is the amplitude profile along the green line, you see that you have the two peaks that correspond to the propagation of spin waves in the two domain walls. And since the two domain walls are separated, here you have a 0 in the amplitude, which means that you actually have the two modes that propagate separate. But then we can use the fact that the domain walls can be moved with the external field. So if we change the external field, then we can make the domain walls a little bit closer. And we, again, measure the amplitude of the spin waves across this line. And you see that they're much closer, the two peaks. And here you start seeing that the amplitude is not 0, which means that they're somehow getting to be in the same place spatially, at least the tails of the spin waves. And then we can reduce the field again a little bit more. And here you have definitely that the two spin waves are actually interacting so that you have basically a spatial superposition of the two spin waves mode that you can control with the external field. And this is was a nice demonstration that you can actually have a functionality that can be modulated in a reversible way. In this case, via external field, exploiting the fact that spin texture are not fixed and immovable, but can be manipulated with external stimuli. So in this case, now I don't have it here, but if you see the phase of this, this point is actually, let's say, consistent with the spin wave interference between the two modes that you have. So you can actually have your modes that can be made interfere in a controlled way, or you can have them far away from each other. And now I come to the last application, which happens in a completely different system. That is the second one that I showed you before. So in a synthetic antiferromagnet, where we have the two ferromagnetic layers that are pointing in opposite direction, one with respect to the other one. And this is somehow, let's say, mutuated from nano-optics. So, and in particular on plasmonics. So probably a lot of you know about plasmonic nanoantennas, where we use a physically patterned, for example, gold rod that is illuminated by a laser light to actually launch plasmons within a material. In this case, I put an example that is in a science paper of some time ago, where they actually can shape the wavefront of the plasmon by shaping the shape of the nanoantenna. So you have this metal rod that can be shaped, and the shape of the launched plasmons are retaining the shape of the rod, of the antenna that generates them. So we perform basically a similar thing, but with magnons and spin textures. So instead of having a golden rod as an antenna, we have a domain wall in this particular material. And this is exactly a curved domain wall where the magnetization on the top part of the chip points towards the right, and on the bottom part of the chip points towards the left. And if we illuminate, let's say, the whole chip with a uniform and, let's say, not highly localized oscillating magnetic field in the gigahertz, then this field actually happens to couple very well only with the structure that we wrote via tam-SPL, so with the domain wall, and actually sets this spin texture in oscillation. And the oscillation of the spin texture is what actually emits spin wave. And as I will show you later, the shape of the magnons of the spin waves that are generated actually matches very well the shape of the spin texture that we wrote. And since we can control very well the topology and the position and the structure of the spin texture, then we can hope to control very well also the shape of the wavefronts and to perform some kind of manipulation on the spin waves that you can generate with the spin texture-based nanoantenna. So here, again, we went to the synchrotron to observe what happens. And here you see some examples. You have a straight domain wall where you have the magnetization on top and on the bottom pointing in opposite direction. And you have that by illuminating, let's say, the spin texture with an oscillating magnetic field, then you can emit this planar wavefronts with a wavelength that in this particular system goes down to, at this frequency, 1.4 gigahertz is roughly 300 nanometers. So you have these wavefronts that actually emanate from the spin texture. If you have a vortex, that are the spin texture that I told you before, that are basically a whirling of the magnetization around a central point, and you excite this vortex, then you have radial wavefronts that propagate exactly as you would have by launching a stone in the lake, for example. And Also, if you shape your nanoantenna with a parabolic shape, for example, you have that the wavefront that are emanating from the domain will actually follow very well the shape of the antenna. And importantly, for spin wave application, it's something that in optics is, well, with plasmon, not so much, but in optics, you have usually a really long propagation distance because the damping of the electromagnetic waves in waveguides is not so much. But one of the problems of magnonics is that in most systems, spin waves dampen really quickly. So the nice thing about this system is that you can actually have spin waves propagating from the nanoantenna for 15, in this case, we observed only 15 because we have the limited acquisition window, but for several times the wavelength. And this is exactly what you need for having interference, and having interference is exactly what you need for being able to use these systems for making computation. So that in this system, you can actually generate your spin waves in a controlled way, so make wavefront engineering, and to have them propagate far away from the antenna for, let's say, a wide distance outside the antenna. This is exactly the spin wave profile along this line. So taken from a snapshot of this image, and you see that you have 14 or 15 times the wavelength in this case. And actually the amplitude is not decaying very much, so we expect that the spin waves are propagating much farther away. You can also combine these emitters for having a controlled interference of spin waves, or you can focus them. So in this case, we took a curved nanoantenna. This is exactly the simulation that I showed you at the beginning. If we curve the wavefronts, we can actually focus the spin, generate a focused and directional spin wave beam that is focused at a certain distance that depends on the curvature of the domain wall. And in this case, we showed that the focusing area is comparable to the wavelength. And in this case, we have a diffraction limited beam. So we have a focusing, let's say, area of roughly 340 nanometers, in this case, away from the antenna. And you can also combine different types of antennas for building a highly controllable interference figure. So in this case, we have a straight domain wall that emits planar wavefronts combined with a vortex that emits radial wavefronts. And you see here that you have the interference maxima here and minima here, this gray region. And here you see the different orders of interference that actually depend on the position of the vortex that you can, if you want, move with the external field or with currents. And in this case, we were able to create this, this controlled interference that you can also modulate with the external field again. So the idea is that then we have all these tools with which we can build some spin wave computation platform that actually exploit spin wave interference for making computation. This is still the next step that we have now. So that now that we more or less know what we can do with this technique, then we will aim to actually combine all the structures in order to be able to have a well-defined goal and to build computing devices, for example. Okay, so with this I come to the to the conclusion. So I showed you that we can, in a wide range of systems, control the spin texture via thermally assisted magnetic scanning probe lithography. And in particular, I showed you something about in-plane systems, out-of-plane systems, and synthetic antiferromagnets. And each one of these systems has particular applications and particular, let's say, peculiarity that you can exploit by using spin textures as active components for manipulating quasi-particles such as fermions or spin waves. And controlling the shape and the geometry of the patterning field and the shape of the patterning area, we can also control the types of textures that you can write, ranging from 2D, two-dimensional domains, to one-dimensional domain walls, and to zero-dimensional topological solitons with a deterministically defined topology. And the application that I showed you was about spin waves. And in particular, I showed you that we were able to manipulate spin waves and have them propagate as in waveguides within domain wall-based circuits or we were able to actually, in synthetic antiferromagnets, emit highly controlled spin wave wavefronts that actually can be combined to build complex interference figures that can be used for spin wave computing. With this, I thank you very much. I thank once again funding and all the people that collaborated, and thank you very much for the attention.